At this very moment, across 13 billion years of cosmic history, a message is arriving. It isn't carried by a spacecraft or encoded in radio waves. It's written in the ancient light of quasars, the most luminous objects in the universe. And it whispers a chilling possibility. The laws of physics are not fixed. In 1997, a team of astronomers led by John Webb, studying the light from a distant quasar designated Q0347-3819, detected a seismic tremor in the foundations of reality. As this quasar's light traveled through intergalactic clouds of gas on its multi-billion-year journey to Earth, atoms in those clouds absorbed specific frequencies, leaving a barcode-like pattern of dark lines in its spectrum. The precise spacing of these lines is governed by one of the most fundamental numbers in nature, the fine structure constant alpha. This dimensionless number, approximately 1 in 137, dictates the strength of the electromagnetic force. It's the master parameter that determines how electrons orbit atomic nuclei, how atoms bond to form molecules, how light interacts with matter. It is, in essence, a critical line of code in the universe's operating system. And according to the data from that quasar and dozens more since, this constant isn't. The Webb team's analysis, published in Physical Review Letters, suggested that in the distant past, alpha was slightly smaller, by about 1 part in 100,000. This is an infinitesimal deviation, but its implications are monumental. For a century, physics has been built upon the Copernican principle, the idea that the laws of nature are the same everywhere and at all times. A varying alpha shatters this bedrock assumption. To understand the mechanism, we must look at the experimental setup. Astronomers use instruments like the Keck telescope in Hawaii, equipped with a high-resolution Echelon spectrometer. This device acts like a cosmic prism, splitting the faint light of a quasar into its constituent colors with exquisite precision. By analyzing the absorption lines from elements like iron, nickel, and silicon in ancient gas clouds, they can measure the value of alpha at that specific time and place in cosmic history. The technique, known as the many-multiplet method, compares the spacing of multiple absorption lines from the same element, a method highly sensitive to any change in alpha. What the data whispered was a spatial dipole. In one direction of the sky, alpha seemed to be slightly smaller in the past, while in the opposite direction, it appeared slightly larger. This wasn't a random fluctuation. It was a structured directional variance. This finding ignited a firestorm of debate and scrutiny. The stakes are almost impossibly high. If alpha changes, then the very nature of matter is unstable. A slightly larger alpha would increase the electrostatic repulsion inside atomic nuclei, potentially making elements like carbon, the basis of all known life, unstable. Stars might not be able to fuse hydrogen into helium, or they might burn through their fuel at a catastrophically different rate. The delicate balance that allows for complex chemistry, for planets, for us, would dissolve. The universe as we know it is a product of this precise value. Its constancy is not just an academic assumption. It is a prerequisite for our existence. Of course, such an extraordinary claim demands extraordinary evidence. Other research groups have pointed to different sources that suggest the opposite. The Oklo Natural Nuclear Reactor, a 2-billion-year-old uranium deposit in Gabon, Africa, that spontaneously underwent fission, provides a powerful terrestrial constraint. The nuclear reactions that occurred there were incredibly sensitive to the value of alpha. Analysis of the fission products, as detailed in studies published in journals like Nature, suggests that alpha has not changed by more than 1 part in 10 million over the last 2 billion years. This creates a profound tension. Are the quasar measurements a subtle systematic error, a ghost in the complex machinery of astronomical observation? Or are the terrestrial measurements like Oklo only telling us about our local cosmic neighborhood, blind to a larger cosmological scale gradient? The possibility remains that the laws of physics are parochial, changing from one cosmic epoch to another, or even from one galactic supercluster to the next. We are left with a universe that is either stubbornly constant, with a few tantalizing but misleading data points, or a universe where the rules are suddenly, terrifyingly in flux. What if this apparent glitch in the cosmic code isn't just a surface-level anomaly? What if it's a symptom of a much deeper, more fundamental instability in the very fabric of space-time itself? From that paradox emerges an even more profound and terrifying prospect. If a fundamental constant can shift, it implies that the state of our universe is not absolute. This leads us to the scariest idea in all of cosmology, the instability of the vacuum. Our entire cosmos, every star, every galaxy, every particle exists within the Higgs field. According to our best understanding from the standard model of particle physics, this field has a certain energy level, a potential. We assume we are at the bottom of the valley, the point of lowest possible energy, a state known as the true vacuum. But what if we're not? What if our universe is perched precariously in a shallow dip on the side of a much larger, deeper valley? This would make our vacuum a false vacuum, a metastable state. It's like a droplet of supercooled water, liquid below its freezing point. It looks stable, but the slightest disturbance can cause it to flash freeze into its true lower energy state, ice. Our universe could be in a similar cosmic state of suspended animation. Calculations based on the precise masses of the Higgs boson and the top quark suggest that our universe is, in fact, terrifyingly close to this line of metastability. It's stable, but perhaps not eternally so. The mechanism for this cosmic self-destruction is called quantum tunneling. At any moment, in any place, a random quantum fluctuation could push a tiny region of the Higgs field over the energy barrier and down into the true vacuum state. This would create a microscopic bubble of new reality. This bubble would not be a gentle transition. It would be a sphere of annihilation, expanding outwards in all directions at the speed of light. Inside the bubble, the laws of physics would be radically different. The new, lower value of the Higgs field would alter the masses of fundamental particles, like electrons and quarks. The fine structure constant, alpha, would likely change dramatically. Atoms as we know them could not form. The complex structures of stars, planets, and life would be instantly and irrevocably erased, replaced by a new alien physics. Because the bubble wall moves at light speed, we would have no warning. One moment, the Andromeda Galaxy would be there, the next, it would be gone, its light and information consumed by the expanding front of the new vacuum. The wave of cosmic erasure would wash over our solar system, our planet, and us before our nervous systems could even register that something had happened. It would be the ultimate, silent death of the universe as we know it. This isn't just theoretical speculation, it's connected to the biggest mystery in modern cosmology, dark energy. The accelerating expansion of the universe, first observed in 1998 through supernova surveys and confirmed by missions like the Planck satellite, is attributed to this mysterious force. In the standard lambda CDM model, dark energy is the cosmological constant, an intrinsic energy of the vacuum itself. But this value is bizarrely small, 120 orders of magnitude smaller than theoretical predictions. This discrepancy is one of the greatest failures of modern physics. However, if our vacuum is a false one, its energy level, our dark energy, might not be constant at all. It could be a dynamic field slowly rolling towards a new minimum. This connects directly to the fate of the cosmos. If dark energy is weakening, the universe's expansion could slow and reverse in a big crunch. If it remains constant, the universe will expand forever into a cold, dark, empty state known as the heat death. But there is a third, more violent possibility. If dark energy is a form of phantom energy that grows stronger over time, it would lead to a big rip. In this scenario, the repulsive force of dark energy would become so strong that in the final moments of the universe, it would overcome gravity, tearing apart galaxies and solar systems. Then it would overcome the electromagnetic force, shredding planets and stars. Finally, it would overwhelm the strong nuclear force itself, ripping apart individual atoms. Both vacuum decay and the Big Rip represent a universe where the fundamental stability we take for granted is an illusion. Our existence is a delicate, temporary equilibrium. We live on a cosmic precipice, balanced between the laws that allow us to be and the ultimate, more stable state of non-existence that awaits. The universe isn't just expanding, it may be unraveling.